Good morning.
Good morning.
Good morning.
Morning.
Good morning.
Morning. Nicole. And okay, goals. So let's so today we're going to start with chapter number 10. And a new topic that we're going to just begin with is going to be what we'll call resolution. Okay, we're going to have different types of resolutions, if you want to put it that way. Okay, so we can go into we can talk about the different types of resolutions that we may discuss in this chapter, and upcoming chapters. Just to briefly make as a comparison. But what's going to be common in all is that they're going to be resolutions. So this is a topic that's going to be be brought up again in primarily in this chapter here, and in some other chapters. But what is a resolution? Resolution means just means accuracy. Okay, accuracy. Now, an example of accuracy can be, let's say, that if you are looking at this pen here, for instance, clear? Now this pen here is one pen or pointer or whatever you want to call it. Clear? Okay, it has a certain shape. Clear? Okay. It also has a certain color. Clear? Okay. Now, if I look at this pen here and to get an accurate view of it, what I ideally should see is a pen that is black. Clear? And as one end is narrow, and as one end is a little bit broader, has a tip. Clear? So that would be me as getting as a accurate image of what I'm looking at. Did that make sense? Clear? Okay, so accurate resolution is made that's going to be we can say the ability of the system to make it a accurate image. Okay, now let's say if I'm looking at this pen here, I'm looking at it, but what I see is as a pen which is not black, but it is white. Or if I, yes, okay, see not one pen, but two pens, black or white, or one black, one white, doesn't really matter. What did that mean? That, okay, yes, I'm seeing something which is not accurate. Okay. Did that make sense? Clear? Okay. If, okay, as I see, yes, okay, this pen here, yes, okay, should approximate, yes, okay, be this big. If I see the pen, well, okay, yes, I see it in the color that it is, okay, that information is correct. But if yes, okay, if the size is reduced, that is going to be inaccurate as well. Or if its size is getting bigger than it actually is, that is going to be inaccurate as well. Okay, so when yes, okay, when you have what we can call as okay, bad or poor resolution. Okay, however we refer to as okay as a bad resolution, a poor resolution, degraded resolution. That is mostly going to lead to as okay what we will call artifacts on an image. Did that make sense? What's going to be an artifact? That's okay. I'm looking at a pen, but what I may see is okay as a key. Right, okay, that's going to be as okay inaccurate. Right, okay, but if I'm looking at a pen and what I see is, let's say, it's okay, a flask or a bottle. That's not accurate. Clear? Okay, so likewise, okay, if you're scanning something, and okay, yes, your image gets okay, or you form, you can call it okay, accurate image, or your system is able to just okay produce an accurate image of the structures that you're scanning. That may mean that okay, you have a good resolution. Did that make sense? Whereas, okay, yes, if it is not accurate, you can say, okay, it's going to be inaccurate, or it's going to be okay, incorrect information that you get on the image. That can be referred to as being as okay, a poor resolution, a degraded resolution. Did that make sense? Okay, now good resolution, well, okay, yes, you get okay as an accurate image. Okay, you're scanning it, okay, as what you see on the image is actually as okay, an accurate representation of the structures that you're scanning. Whereas, okay, if you have a poor resolution, okay, in whatever form, whatever reason, that is poor resolution is mainly as okay, going to lead to what we will call artifacts. Clear? Okay. So, but artifacts, that's okay. That's a topic that we actually is okay. We'll be discussing very, 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 yes, okay, towards the very end of this this whole course here. Okay. But just keep in mind, girls, poor resolutions will lead to artifacts on your image. What's going to be artifact? You can maybe say, okay, that you see things on the image which is not accurate. Okay, what can be as okay, the reason for as okay, we can say as okay, these inaccuracies on the image. Most of them, yes, okay, may be due to poor resolutions. Okay, some artifacts, yes, okay, you may not, well, okay, you can say it's okay, even though we call it an artifact, but they may have a, you can say it's okay, clinical important value. Okay, some artifacts are just going to be there, and okay, yes, the only thing that you need to know is, well, okay, this is not actual, this is okay as just a result of an artifact. Okay, but poor resolutions will lead to artifact. And what was art resolution? We can mainly say, okay, what it mainly as okay just means is accuracy. Clear? Okay, okay. Or we can say, okay, the system's ability to produce images with accuracy or accurate images. Okay, that will be referred to as a resolution. Okay, so if you see something that, for instance, okay, is round, or you're scanning a structure that is round, and you see that structure on your image, which is round as well. Okay, not just round, but yes, okay, the size is also accurate. Let's say it's okay, the physical is okay, this measure, let's say it's okay, 2 millimeters. And what you see on your image is also it's okay going to measure 2 millimeters on your image. That is accurate. Okay, had it been, let's say it's okay, measuring 20 millimeters on your image, that would have been inaccurate. Or because that would have been okay as a poor resolution or degraded resolution. Did that make sense? Clear? Okay. If we, for instance, say that's okay, well, okay, we were scanning one structure. It is 2 millimeters. Okay, good. Okay. We may see as okay a structure here, yes, okay, which also is okay. We can say it's okay, measure 2 millimeters. But then we actually, it's okay, see a copy of the structure here as well. Although it's okay, physically, there was only as okay, say one of these circular structures present, but if you see 2 instead of 1, there's again going to be, it's okay, what we call a poor resolution. So this will again, it's okay, be an example of an artifact. Okay. Did that make sense? So we can mainly say it's okay that, oopsie, sorry. We can have, okay, as resolutions, which is good. And what does that mean? That will mainly mean that, okay, yes, the image or the information that we see on the image is accurate. Whereas, okay, on the other hand, we can have, okay, yes, poor resolutions. Okay. Poor resolution. And what would that mean? That would mainly mean that, okay, yes, some of the image that we see on the, or okay, some of the things that we see on the image is inaccurate. What does it mean to be inaccurate? That would mean it be a poor resolution. And mainly would mean, well, okay, the things that we see on the image is not an actual presentation of it's okay, the structures that we have measured, it's okay, scanned. Did that make sense?
Yes, it did.
Good. Okay. Now, please keep in mind, girl, yes, okay, resolution or accuracy doesn't mean that you're going to get, yes, okay, a crisp picture. Okay. What you may, yes, okay, will see or use my, yes, okay, sense that yesterday, that, okay, yes, your images may just be, as okay, a collection of different shadows. Okay. So it's not going to be, as you can say, so accuracy or resolution doesn't mean quality. It just means because you can still have, okay, as a picture that may look crisp and nice to your eyes, but the information that you're getting is not accurate. So you will still have, okay, as a poor resolution. Okay, you can have the crappiest quality of the picture, but at least that's okay, you have a good resolution because, well, okay, you scan a structure which was okay as round and it had okay as a measurement of, let's say, 2 millimeters, and it shows up at 2 millimeters. Yeah, so that can still be as okay, that will still be accurate, although you say, well, okay, the picture quality is not the best. Well, okay, so please, girls, resolution does not meet or does not mean quality. Okay. Any question about what a resolution is? Okay, so this is made as okay, going to be as okay a topic. Okay, we'll talk about 2 of the main resolutions here in this chapter. Okay, we will come across okay as other kind of resolution, which is going to be as okay in chapter 13. we're going to just, okay, talk about another resolution in chapter 14. Okay, we will even have, okay, other kind of resolutions in chapter 15. So you can see as, okay, this topic of resolution here is going to be brought up again and again and again. Okay, so if there's anybody who does not know what resolution means now, yes, okay, please speak up. So accurate. Okay, and what's going to be accuracy? Yes, okay. If you look at a pen, you want to be able to say, well, okay, yes, this is a pen or pointer or whatever. It's black. This is the shape that it has. Okay, so and so, and this is the size. Okay, so that'll be as okay the information that you ideally is okay accurately want to be able to see on the image. If you still see the pen, well, okay, yes, it has this shape. But if its size has changed, that's going to be inaccurate. Clear? Here you can see as okay, the pen is black. If it shows up in okay as something that may represent another color than black, that is going to be inaccurate. Clear? If you're looking at just one pen and you see 2 pens or 3 pens or 5 pens, okay, that is again going to be inaccurate. Okay, so things that are going to be inaccurate, that's okay. In the first place, we can say, okay, that will be as okay due to poor resolutions. Clear? Okay, poor or bad resolution of that kind of a type of resolution. And what that will lead to on an image is going to, as okay, as a whole be referred to as an artifact. Okay, so artifact, that's okay, a whole separate topic. We will talk about some common artifacts in chapter 21, which is just about, yes, okay, different kinds of artifacts. Now, girls, what we pretty much can do is okay when we talk resolutions. What we pretty much can do is okay, we can mainly say okay that we have 2 major types of resolutions. Okay, just like we had 2 major types of intensities. One is going to, yes, okay, be referred to as resolutions of space. So that'll be as okay what we'll call spatial resolutions. Yeah, okay. And why do we as okay use the term yes, okay, spatial resolution mainly as okay because these resolutions here are going to be measured in space, or mainly as okay, using a unit of distance to determine these resolutions here. Clear? Then you can just okay, and I said just okay, just like we had an intensity, the other one is going to be as okay, temporal resolutions. So temporal resolution, it means it's okay because okay, we're going to just okay measure things or determine it's okay the resolution in terms of time. Okay, goals. Now this temporal resolution, yes, okay, we're going to just okay talk about specifically that one in chapter 13. Okay, so your whole chapter 13 is mainly as okay about temporal resolutions. Clear? Okay, so accuracy of you can say is okay, you're recording in terms of time. Okay. Clear? Where the other is what you can call as, okay, spatial resolutions. So spatial resolution is the accuracy of your image. This is measured in space or by units of distance. Did you girls get that? Okay, so your temporal resolution, that is going to is okay, be chapter 13. We will do that in, okay, as a week or a half or two. Okay, and as I said to some of the girls yesterday, it's okay, this is okay, a very, very is okay, important chapter. Now goes, when you say it's okay, spatial resolutions. Now, primarily as okay, when we talk about spatial resolutions, that are going to it's okay, we are going to have some different types of spatial resolutions. Two of them is what we have in this chapter here. So the first one we can say is okay, is going to be as okay, your axial resolution. Clear? Now that mainly is okay, just will say as we can mean is okay. The next one is going to be as okay, what we call the lateral resolution. Clear? Okay, so these are mainly as okay, the two resolutions that we talk about here in chapter 10. Then go just okay, that's going to be as okay, another resolution, which is still going to be as okay, considered a spatial resolution, and we may as okay call that one the elevational resolution. Clear? This fellow here is okay, that will be as okay in chapter 12, right? That's okay. Yeah, chapter 12. Then, okay, yes, now strange enough, yes, okay, there is a special resolution that is going to, yes, okay, be called, okay, as a spatial resolution. We will talk about this fellow, yes, okay, here in chapter 15. And in chapter 15 and 16 is going to be, yes, okay, a last type of spatial resolution, which will be, yes, okay, what we will call a contrast resolution. That's going to be, yes, okay, chapter 15 and chapter 16. But primarily, as okay, if we divide your resolutions into two major types, we can say, okay, we have resolutions pertaining or yes, okay, related to space, or area, or distance. We have, yes, okay, resolutions pertaining or related to time, which is respectively going to be spatial resolution and temporal resolution. In the spatial resolutions, we have lateral resolution, axial resolution, elevational resolution, spatial resolution, and contrast resolution. Okay. Whereas for temporal resolution, that's mainly okay, there's going to be the kind of resolution that we'll be looking for in case of, or it's okay, we'll be using. Mainly it's okay if you are scanning an object that is moving. Either moving from place to place to place to place, or that's okay, standing in one place and actually that's okay, may changes the shape as we go. Right, okay. So yes, okay, you can already say that, okay, yes, scanning a beating heart will require, yes, okay, a good temporal resolution because it is moving. Okay. Or moving on, we can say it's okay, changing its shape. From split of a second to split of a second from split of a second. Okay, girls? Good. Now, ladies, before, yes, okay, going into, yes, okay, the different two resolutions of this chapter here. I just want you, yes, okay, do a slide comparison of these three resolutions here. Okay, so girls, if you want to, yes, okay, get a blank piece of paper. Okay, get a blank piece of paper and mainly, yes, okay, just write this. Resolution. Or yes, okay, for the resolution, that's going to be, yes, okay, something that we'll call a numerical value. Right, okay. And here we can just say it's okay. Accuracy. Now, girls, the three resolutions that I said that I wanted to talk about or refer to was respectively. Okay, let's do this one. What we, yes, okay, we'll call the axial resolution. Okay. Now, what you go, just okay, we'll find out that, okay, as the axial resolution goes, under other names as well. So it will also just, okay, be called the longitudinal resolution. We may also call it as, okay, range resolution. We may also call it as, okay, radial resolution. And it may also, it's okay, be called depth resolution. So these are all, yes, okay, different names for your axial resolution. Okay, the book will primarily is okay refer to as the axial resolution, but it also goes under other names. Right, okay. So yes, okay, you guys will have to, yes, okay, remember these names here as well as being, yes, okay, what is also referred to as the axial resolution. Is that clear? Now the next resolution that I said that that's what I mean, it's okay, because we're just going to just okay do a comparison between these three here. Is okay as what we primarily as okay, what the book primarily is okay referred to as the lateral resolution. Okay. Now this lateral resolution, yes, okay, just like your axial resolution also can be referred to by different names, which is going to be as okay, angular resolution. It may also be referred to as okay as the transverse resolution. And okay, yes, it may also be called, yes, okay, the azimuthal resolution. So pretty much, okay, yes, other names which I okay, also refer to as okay, your lateral resolution. Clear? No, it's okay. We're going to cover all these. It's okay again. Yes, okay. Once we talk about it's okay, the lateral resolution as a separate topic. The last one that I said I want to talk about, or it's okay, mean it's okay, refer to was the elevation resolution. And okay, yeah, that has okay as a weird other name. Slice thickness resolution. And some of you guys will be saying, well, okay, we are here to just okay, learn how to do ultrasound, not how to slice a piece of bread. But that's mainly as okay, just the name that it also goes under. Personally, it's okay. I don't like this name. I think it's yes, okay, a little bit ill presenting, yes, okay, what this resolution here is about. But it's not about my liking or non-liking. You still have to remember that, okay, yes, the elevation resolution can also be referred to as the slice thickness resolution. Clear? Now, girls, as we go through these three resolutions here, at some point, yes, okay, we will say it's okay, each of these resolutions here are going to have a numerical value. Clear? Okay. What the numerical value for your, let's okay, exit resolution, how that is going to be determined. We will talk about that when we get to that. Oh, yes, okay, the yes, okay, numerical value of your lateral resolution is determined. We will talk about that when we get to that. And yes, okay, for your elevation resolution. Oh, yes, okay, this numerical value here is going to be determined by for yes, okay, each of these resolutions. We will talk individually about them when we get to that point. But generally speaking, goes as far as okay, as when comparing as okay, the numerical values of these three resolutions here, your exit resolution is always going to have okay, yes, the lowest numerical value. So if you compare as okay, the numerical of the value of exit resolution against lateral resolution against elevation resolution, exit resolution will always have the lowest numerical value. Okay. And what would that mean? That would mean that this is actually just okay going to the best of these three resolutions here. So it's okay when we compare as okay these three resolutions, say which of these three resolutions here gives us the best resolution, or we can say the most accurate information is going to be as okay your exit resolution. It's always going to be as okay the best out of these three here. Okay, we can just make a jump because we can mainly say as okay, your elevation resolution or slice thickness resolution, out of these three resolutions here, that is always going to as okay be the highest numerical value. And what this highest numerical value is going to lead to that, okay, as when looking at these three resolutions, this is going to be as okay, we can say it's okay, the poorest. Poorest or worst. which mainly means, okay, there is going to be, okay, a greater likelihood for, yes, okay, your slice thickness or elevation resolution to be inaccurate compared to the axial resolution and even compared to the lateral resolution. Because we can mean as, okay, for the lateral resolution, we can say as, okay, the numerical value is going to be as, okay, greater than the axial resolution. But most likely as, okay, is going to, as, okay, be lesser than the elevation resolution. Which mainly mean that, okay, yes, is going to be as, okay, poor resolution than, well, okay, yes, we can say axial resolution. But it's going to, as, okay, we can say as, okay, be better than the elevation resolution. Okay, so for these three resolutions, what we mainly see is, okay, that the numerical value, the lower numerical value will always give you, as, okay, a better resolution. The higher the numerical value gets, it will lead to, as, okay, a poorer and poorest resolution. Did everybody get that?
Yes.
So what can we say based on that? Well, okay, as the numerical value is going to be, as, okay, inversely proportional to the resolution. Higher numerical value, lower resolution or poor resolution, and vice versa. Because the resolution or the kind of resolution which has the lowest numerical value will have the best resolution. Clear? Or you can say, okay, the lower the numerical value, the better will be the resolution. Now goes, anybody has any question about, yes, okay, what a resolution was?
So that means they're inversely related, right? Numerical value and accuracy.
Exactly.
Okay, thank
Okay.
you.
Because
I'm sorry. So you said the numerical value and the accuracy is inversely?
Yeah.
Oh, okay, sorry. I put the wrong one.
because you, if you look at the chart that we just made right here, look here. What did I say for your axial resolution? When comparing these three here, that was the one that is going to have as, okay, the lowest numerical value. Right?
Yes.
Right. So that is going to be, okay, out of these three resolutions, yes, okay, as per standard will be, yes, okay, the best resolution. Or we can say, okay, best or most accurate. When comparing, yes, okay, these three resolutions. Where, okay, on the other hand, we say, yes, okay, elevation resolution for 99% of your transducers, where, okay, I have the highest numerical value. And that mainly cause that, okay, yes, out of these three resolutions, yes, okay, the elevational resolution is going to be the poorest. What does the poorest resolution mean? Yes, okay, it's going to be least accurate. Right? So higher, yes, okay, lower numerical value, best accuracy. Highest numerical value, lowest accuracy. Did that make sense?
Yes.
Clear? Okay. But then, yes, okay, within each resolution, you may, yes, okay, we can say, yes, okay, we have, yes, okay, two, let's say, okay, examples of, okay, yes, exit resolutions. Okay, where one exit resolution have a high numerical value and that one other one is going to have a low numerical value that we calculate or determine as, okay, within the exit resolution, this is a high numerical value. Within the exit resolution, this is a low numerical value. Now again, yes, okay, it's going to be out of those two, the one that has the lowest numerical value that will be, yes, okay, more accurate. So even within the resolution itself, the lower numerical value, the more accurate it is that resolution will be. Clear? How we determine these, yes, okay, numerical values, we will get to that once we get to, yes, okay, each of the resolutions. But what I mean is, okay, just wanted to give you here was a rough comparison between, yes, okay, these three spatial resolutions here. Exit resolution, lateral resolution. We're going to be talking about these two fellows here in this chapter. Elevational resolution is going to, yes, okay, be brought up in chapter 12. Clear? Okay. Now, girlies, any questions?
No.
Any questions? Okay, so just keep this one here handy. Okay, this chart or piece of paper or index card or whatever, just keep that one handy because, okay, we can always, okay, put in info. Okay, or you can always add, yes, okay, newer things to it. Okay, girls. The first resolution is going to be, yes, okay, the spatial resolution. Clear. And what did we mean to say? It's okay that the spatial resolution or axial resolution, sorry. Now, what did we say that, okay, as a resolution was going to mean? We can mean it's okay, say, okay, the ability of the system to accurately display structures. Right? That now, guys, personally, I don't like this definition here, but anyways, that's okay. That's how your book wrote it. Are parallel to the beam's main axis. Okay. Now, if you look on page 145, when it talks of, okay, as paragraphs, okay, axial resolution. Yes. And axial here is going to be, okay, this parallel to the beam's main axis. Okay, so you can actually see that, okay, yes, that is written in bold letters. Okay, now goes the question may arise, okay, yes, what in the is the beam's main axis? Now goes, just look here. We say, okay, if this here is, okay, was your transducer. And what did we have? We can say, okay, we have a beam. Right? And in your beam, we can mainly say, okay, that this is going to be, okay, your beam's main axis. Oh, yes, okay, as you saw yesterday, practically, yes, okay, when we are scanning. Okay. We can say, okay, that's okay. Let's just say that we is, okay, use curvilinear transducer. So what your beam main is going to be going is, this is how your beam goes. Okay. Whereas, okay, it may, yes, okay, focus at a certain point. Yes, okay, we can say, okay, that was here. But right now, yes, okay, for your axial resolution, yes, okay, your focus is really not that important. Now, what we mean, you can say that the axial resolution is going to be is, or if you just look at, okay, as the different names that it goes under. And okay, as one of the names that I like the most is, okay, as depth resolution. Because you may say it's okay that you have a structure. Let's say it's okay at this depth here. Clear. You may have, let's say it's okay, another structure at this depth here. Okay, when we look at it, we can mainly say it's okay that the red structure here is okay, that is at a shallow depth. Right, okay. Whereas, okay, as this green structure here is at a deeper depth. Did that make sense? Did that make sense?
Yes.
Yeah. Good. Okay, so that's why it's okay. You can make okay, it's okay. The word depth resolution. I like that more. Okay. Because okay, it actually tells us okay what this main resolution is about. And what do we mean by resolution? Means okay, just the ability of a system to accurately display structures. Right here is okay, we have two structures. We can say one was at a shallow depth, the other one was at a deeper depth. That's we can say is okay how they physically as okay are located. Clear. So we have a structure at a greater depth. We have a structure at a deeper depth. Now we can mainly say that, okay, yes, in this instance here, if these two structures here are shown up as two separate structures, that we scan them like this, and they show up on the image like this, that will be as okay, a good exit resolution. Or a good depth resolution, because our system was able to distinctly as okay show these two structures here, or these two structures here as two different structures on your image. So that may mean that okay, as we have a good exit resolution or depth resolution, because what has to be is okay, what's the point here? Now one structure gotta be superficial, the other one has to be deep. Okay, so mainly that's okay because it's a resolution that okay, yes, distinguish structures in depth from one another. That's why we call it okay, can also refer it to as depth resolution. Did that make sense?
So I have a question. So for the depth resolution, it is basically showing where the shallow depth and where's the deeper depth.
No, what my dear, it has to listen. And that's why I say it's okay. Do you mind if I go to another slide?
Go ahead.
Look there. Let's say it's okay, this is the area that you're scanning. Clear. Picamini says, okay, now practically it's okay, what you will be doing is it's okay, you can say it's okay, this is where you place your transducer. Right, okay. Now what do we have here? Yes, okay, we have two structures. We have this structure here, which you look at, okay, will be as okay at a shallow depth. Did that make sense?
Yes.
Mainly because, okay, what we will have deeper to this one here is going to be, let's say, okay, this structure here. Which we mean as, okay, we just say as, okay, it's at a deeper depth or at a greater depth, right?
Okay.
Clear?
Yes.
Good. Now, when you are scanning this, and your scan, let's say it's okay, shows up like this, that you actually as okay are able to distinguishly see this shallow structure here and this deep structure here. If they show up distinctly. Or then you say, well, okay, I saw two structures, or it's okay, I'm scanning two structures, and they show up as two separate structures. Now, I mean, in this case, as okay, mean that okay, as we have a good, as okay, what we can call as okay, exit resolution. Where the whole point of the exit resolution is that it's going to as okay be able to separate structures from one another, or as okay, shown it distinctly as okay, structures that lie superficially deeper. So you can go on and say, okay, if okay, as we have something here, we had okay, as something here, and okay, as they also as okay showed up as distinct structures on your scan. Picamini says, okay, blue is superficial, red is deeper, purple or pink is even deeper, green is deepest, right?
Okay.
right?
Okay, yeah, I get it.
And
More.
you are able to, yes, okay. And the system is able to, yes, okay, show these structures that lie deeper and deeper and deeper and deeper to one another. Distinctly down mean, yes, okay, that you have a good exit resolution. Or, yes, okay, we also could call, yes, okay, this exit resolution could also be referred to as a depth resolution, which mainly means, yes, okay, the ability to show structures distinctly in depth.
Okay,
Clear? But then, yes, okay, it also has these other names, which also okay, has longitudinal resolution, range resolution, and radial resolution. Mainly, you can say, yes, okay, why longitudinal? Yes, okay, because, okay, it runs along the axis of the main axis of the beam. Or we can say, okay, distinct structures along the main axis of the beam. Because, okay, because, okay, if this was your beam, well, it's okay, because if this is the main axis of your beam, you can mainly say, okay, that your beam may, yes, okay, you can say, okay, go like this, for instance. Because I say, okay, at this point, as okay, we have me as okay, just focused on this one here. Although, yes, okay, your lateral, sorry, not lateral, your axial resolution is not going to be affected by the focus. Or practically, it is not going to be the beam or characteristics of the beam that will determine your axial resolution. Okay. It's made as okay, we can just say as okay, the ability of the system to, yes, okay, distinguish structures which are deeper and deeper and deeper to one another. Okay, or as your book may even, yes, okay, refer to, yes, okay, place, positioned back to front. If you look in your, okay, says okay, they may says okay, ability to distinguish structures parallel to the beam's main axis. Or as I will say, as okay, more accurately or more correctly speaking, ability of the system to, yes, okay, distinguish structures that lie superficial, deeper and deeper and deeper and deeper to one another. Okay, because as the sound beam, yes, okay, or practically, yes, okay, your pulse will, yes, okay, travel deeper and deeper and deeper. It's going to come across different structures. And if the system is able to say, well, okay, display those structures separately or distinctiously on your scan, you can say, okay, this is a good resolution. But what kind of resolution? Good axial resolution. Why? Because it's going to be able to just, okay, distinguish structures from one another that is related to one another in depth. Did that make sense?
yes.
Right, okay. Now this is one of, yes, okay, this is one of those chapters that I really have would like to just, okay, had done in the classroom. Okay, okay. But you can mainly say as, okay, you are sitting in rows, right? There's a front row, there's, okay, as another row, another row, another row, another row. Right, okay. On each chair, yes, okay, is one of you sitting. Now, if I look down, let's say, okay, one row of students and say, well, okay, as there are 5 chairs and 5 desks or tables or whatever, right? Okay. And I'm able to say, okay, well, in the front row, This is the person that's sitting. I can see her, yes, okay, clearly and distinctly. Or we can say, it's okay, not being smushed up with the person who sits behind her or him, and so on. So, okay, so if I can look down a row of students and say, well, okay, in first row, this is who is sitting, second row, second line, third, so on, so on, so. That's me as okay, having a good exit resolution. Because in the front seat, I saw, okay, it's Astrid, then it's Shakila, that's Marissa, then it was, okay, who was sitting next? Alexandra, for instance. In that central row. So that will be, yes, okay, a good exit resolution. Did that make sense? Right? Whereas, okay, on the other hand, what could we say, yes, okay, will be, yes, okay, a bad exit resolution here? Or this because, yes, okay, if, yes, okay, these structures that, okay, that we were scanning here, yes, okay, shows up like this. This would be, yes, okay, a good exit resolution, or a good depth resolution, good longitudinal resolution, good radial resolution, good range resolution. Clear? Whereas, okay, if we were scanning the same area, right, okay, but I can say, yes, okay, part of the blue, or the blue would be smushed with the red. Because okay, some of the red is going to, yes, okay, yes, okay, be smushed with the purple. Some of the purple is even, yes, okay, going to, we can say, it's okay, purple, sorry. I'm trying to colorblind now. The pink is going to, yes, okay, be smushed with the green. What is that? Well, girls, this is going to be, as okay, what we just recall as okay, a poor exit resolution. Or we can say it's okay, a poor or degraded depth resolution. Or yes, okay, radial resolution. Or range resolution, or longitudinal resolution. Why? Because let's say that, okay, yes, if I look down that line and it looks like, okay, let's just say that, okay, yes, to me, it looked like, okay, yes, you were wearing Astrid's clothes. Or the girl sitting behind Astrid, yes, okay, it looked to me as you were wearing her clothes. Okay, your bag, the person sitting behind Astrid, her bag or purse or notebook or whatever appear to be as okay on somebody else's table. Okay, something like that. Or yes, okay, I can't distinguish that, okay, as this was Astrid, this was Shakila, this was Marissa, this was Alexandra. But oh yes, okay, smushed up together. But why is okay, one sits closer, other one is deeper, other one is deeper, other one is deeper. So my ability, or yes, okay, we can say it's okay, inability to distinguish between those students as I look down the row is going to be as okay, would have been an example of a poor resolution. Or where you mainly can say as okay here, as I said, the red is going to, yes, okay, be mixed with the blue. and red is going to be mixed with pink, and pink is going to also be mixed with green. So you get something like this when you scan something that practically is okay, well, looking like that, that will be as okay, poor exit resolution, or a poor depth resolution, or a poor radial resolution, or range resolution, or longitudinal resolution. Did that make sense?
Yes.
Yes.
Okay. Any questions? Okay. Any questions at this point here?
No.
Good. Now, ladies, as I said earlier, here, especially that's okay. Especially that's okay, these three resolutions here. Just keep in mind, okay, that we call them as okay spatial because they're going to be measured in using a unit of distance, space, area, etc., etc. Okay, so the unit of your spatial axial resolution, or actually that's okay, will become yes, okay, the unit that occurs its numerical value is going to be expressed as is going to just okay be expressed in the unit of distance. So your axial resolution is going to just okay be expressed in a unit of distance, which can be as okay millimeters. It can be centimeters. Well, okay, as long as okay it's any unit of distance, or we can say okay length. Okay, but right here is okay. There's length here. I mean, or mean, physical length. Clear? Is that? Did you guys get that? Now comes the real stuff, because what determines the exit resolution. Okay, girls, please just keep in mind, okay, when I write AR, that's me, that's okay, just my short form for exit resolution. Okay, it doesn't mean automatic rifle. Okay, so that's just going to be as okay, my abbreviation for exit resolution. So what is going to is okay determine your exit resolution? Or we can mean it as okay to be more accurate or more correctly, the numerical value of the exit resolution. Now that is going to be as okay, we can say it's okay determined by the pulse. Yeah. What component of the pulse? As I said, the length of the pulse. And what did we call the physical length of the pulse? We call that the spatial pulse length. So it's actually going to be as okay, your spatial pulse length that will determine the numerical value of your axial resolution. And where it's going to be as okay, that numerical value of your axial resolution related to, yes, okay, or compared to, yes, okay, we can say it's okay, the distance between two structures that may be as okay at a shallow depth and okay as at a deep depth. Or actually that's okay, this distance here compared to, yes, okay, the numerical value of your axial resolution, where this numerical value is going to, yes, okay, be dependent upon, yes, okay, the spatial pulse length that will determine whether we end up with a good axial resolution or a poor axial resolution.
I was listening, but can you explain that one more again? The numerical value.
Yes, listen here. What is mainly going to say, listen, what mainly is going to just, okay, determine your axial resolution. The main factor that's going to just, okay, determine your axial resolution is going to be as okay, be your spatial pulse length. Why? I told you goes here. Therefore, as okay, for all your spatial resolutions, they are always going to just okay, especially as okay, these three fellows here are always going to be as okay, measured using okay as a unit of distance or area or length. Is that clear?
Yes.
Good. So that's why we say yes, okay, for your space, for your axial resolution, we made as okay, I'm just going to as okay, measure that in a unit of distance or length. Clear? Now, what we mainly will say is okay, now when we talk about is okay, a distance or a length, that's okay, anything that is measured in space, because that's what we mean to be spatial. Okay. What spatial component is going to just okay determine your axial resolution? It is going to be as okay your spatial pulse length. What was the spatial pulse length? That we say is okay, we have a pulse. What was a pulse? A certain number of cycles, right? Okay, but when we measure from here to here in terms of a unit of distance, centimeter, millimeters, micrometers, whatsoever. This distance here is okay, that was what we call a spatial pulse length. Clear? Okay. So your axial resolution is still going, yes, okay, is going to, yes, okay, primarily, yes, okay, be determined by the pulse. What part of the pulse? The spatial pulse length. Mainly, yes, okay, how physically long is it that a pulse is? Clear? Right. So your spatial pulse length, that is mean, yes, okay, what it will be determining, yes, okay, your that numerical value of your axial resolution. Okay, where we can say it's okay, now we may have a pulse, but let's say it's okay, short spatial pulse length. Or yes, okay, we can say it's okay, we may have a pulse with, let's say it's okay, great spatial pulse length. Clear? So this spatial pulse length here, whether short or long, is going to just determine whether you will have a lower numerical value for the axial resolution, or whether you will have a great numerical value for your axial resolution.
So what is the relationship between the numeric value and the spatial pulse length? Is they directly?
You can put it that way.
Okay.
Clear? Okay. But then, yes, okay, now the numerical value, whether short or long, okay, whether you have a short numerical or whether you have, as a low numerical value or whether you have a high numerical value. Is yes, okay, still going to, yes, okay, and what will determine, yes, okay, whether you, yes, okay, get a good axial resolution or bad axial resolution is going to be, yes, okay, comparing or be compared to, yes, okay, the distance between, yes, okay, two structures. Where we can say, okay, one structure was shallow and one structure was deep. So yes, okay, your numerical value compared to the distance between two structures, shallow or deep, or front or behind one another, as your book may even word it, will determine whether your resolution or your axial resolution is going to be good or whether your axial resolution is going to be bad. Did that make sense?
Yes.
Okay. Now, girls, the axial resolution, or we can say, okay, the numerical value of your axial resolution. How do we calculate that? We can say the axial resolution's numerical value. It's really not rocket science. Okay. So your axial resolution, numerical value, is made as okay, that's going to be as okay, your spatial pulse length divided by 2. Where you mainly can say as okay, we had a pulse with a great pulse length. Or we can say, okay, a long pulse. Let's say that, okay, this pulse here was, let's say it's okay, 8 millimeters long. Well, okay, the numerical value for this 8 millimeter pulse here, or the axial resolution for this 8 millimeter pulse here will be 8 divided by 2, which would be 4 millimeters. Clear? But that's still going to be, yes, okay, we can say, okay, a great numerical value if you compare it to, yes, okay, let's say a pulse with a shorter spatial pulse. Let's say that, okay, as we had a pulse length of, okay, as 4 millimeters, which is going to be, okay, a shorter pulse. But that shorter pulse says, okay, if you divide 4 by 2, what do you get? The numerical value for your pulse, for your axial resolution But this pulse here is going to be, it's okay, 2 millimeters. Did you girls get that?
Mhm.
Right, okay. So you can still say, yes, okay, longer pulse, greater numerical value of the axial resolution, right? Right?
Right.
Good. Shorter pulse, lower numerical value for your axial resolution. Did that make sense?
Mhm. Yes.
Right, okay. Okay. Now just comes because that's okay, as I said, to determine yes, okay, whether okay as this long or short pulse here will give us okay as either good axial resolutions or bad axial resolutions. It's all going to yes, okay, be when you compare the numerical value of your axial resolution to the distance between these two structures here, where one structure has to be as okay shallow and the other has to be at a greater depth. So one is going to as okay be shallow, one is going to be deeper. Or as your book says, front and back. Did that make sense? No, we can mainly just okay, just say take the example here and say it's okay that the distance between is okay this shallow structure here. And okay, as we may have okay as a deep structure here. Clear? Let's just say that this distance here, for instance, is okay is the distance between these two structures here was 2 millimeters. That will mainly mean that if we had a transducer that produced a pulse of 4 millimeters, or you could say, okay, or a pulse that had a spatial pulse length of 4 millimeters. That spatial pulse length of 4 millimeters gave us a numerical value for the axial resolution of 2 millimeters. But that mainly will mean that, okay, yes, when that pulse comes, it will go back. Then it comes, and then go back. Okay, so mainly because, okay, the distance between the two structures here is either equal or greater than the numerical value of the pulse. This would have given us, okay, as a good axial resolution. Whereas, okay, as for, let's say, it's okay, the same structures. But, okay, and we can say as, okay, the same distance here is okay, which was okay as 2 millimeters. But if we say, yes, okay, a 4 millimeters, it's okay. If we had a pulse of 8 millimeters, where the numerical value for our axial resolution becomes half of that, which is still 4 millimeters. Or where you can say, okay, 4 millimeters is going to be greater than the distance between these two structures here, which was just 2 millimeters apart. What you mainly can say is, okay, when this big pulse comes, then it goes back. And what it mainly as okay will do is it will register this green shade here, or brown shade, sorry, here. And okay, as this deeper green shade here as one reflection. So yes, okay, they are not going to be as okay distinguished from one another. They may actually as okay be smushed together. So that may mean that okay, as in this instance, yes, okay, what is it that we have? That will be yes, okay, poor EXA resolution. Why? Mainly because okay, the numerical value of our EXA resolution was greater than the distance between these two structures here. Where one is going to be okay shallow and one is going to be deep. Did that make sense? So that's why, yes, okay, if I was looking down the road, and okay, if I was a pulse of a shorter length, okay, what is it I would do? I may okay, just say, it's okay, travel up to the first desk, then come back. Bring the information that I get from it's okay, the girl sitting at the first desk, bring that back to the system and the system will process that. Then I go to the next desk. Then I go to the next desk. Mainly because, okay, I was a short pulse. And what happens as a result of that? I create image, I pick up image information from each desk. Whereas, okay, if I was a long pulse, as I travel, I may as okay cover the area of, let's say, 2 desks or 3 desks before I come back. And all that information is going to be okay, be smushed up together. Okay. Did that make any sense? Anybody got anything to say?
Nope.
I have a question.
Yeah.
So it's based on the numerical value of the AR. If the numerical value is equal to the distance between the shallow and the deep structures, it makes it a good.
No.
No.
Numerical value, yeah. Listen, if the numerical value of your resolution, okay, now since here we talk about EXA resolution, what the EXA resolution was about was to distinguish structures from one another that lie superficially and deep. That relation is important, and that's why I say, yes, okay, I like the word depth resolution. Clear? Because resolution means it's okay, ability to it's okay, accurately display in terms of depth. Clear? or distinguish as okay a structure which is shallow at a shallow depth from a structure which is at a deep depth from another. That will be as okay the resolution. Or you can say okay, that will be a good exit resolution. Because bad is going to be as okay, not able to distinguish. What? Because they are smushed up together. Right? Okay. Now, one thing that you have to remember is okay is when yes, okay, looking at the numerical value. Now, what we just said here was the numerical value for your exit resolution. Well, first of all, yes, okay, let's just get clear out that okay, yes, your exit resolution is going to be a resolution which is going to yes, okay, be determined by your pulse. So it's going to be, okay, your pulse that will determine the exit resolution. Clear? Or you can say, okay, the numerical value of your exit resolution is going to be, okay, determined by the pulse. What part of the pulse mainly? You can say, okay, the spatial pulse length. Because the physical measurement of how long or short a pulse was what we call the spatial pulse length. Clear? So taking yes, okay, your spatial pulse length and dividing that by 2 will give you the numerical value of your exit resolution. You have a pulse which was, let's say, yes, okay, 10 millimeters long. The numerical value for your exit resolution in that case would be 5 millimeters. You had a pulse which was 2 millimeters long. Your numerical value for the exit resolution in that case is going to be 1 millimeter. What would that mean? That as long as there is, let's say, okay, for the long pulse, we should say was 10 millimeters, but the numerical value came down of the exit resolution came down to 5 millimeters. Okay, so as long as the distance between those two structures, one shallow, one deep, is 5 millimeters or more, that pulse will still give you, yes, okay, a good exit resolution. Did that make sense? But if your numerical value of your exit resolution was 5 millimeters, and the distance between the structures was less than 5 millimeters, that pulse would give you a poor exit resolution. Did that make sense? Because we can mainly say, okay, if the numerical value, just write it down that way, or that way. If the numerical value of your resolution or spatial resolutions, the 3 resolutions that I made a comparison of, is greater than the distance between the structures, that will lead to a poor resolution. So if the numerical value of the resolution is greater than the distance between the structures, that will give you as okay a poor resolution. Clear? Okay. Now in exit resolution, what is that distance going to be? The distance between yes, okay, a structure that lies at a shallow depth versus deep. That's why we call it as okay depth resolution. That's pretty much okay as why I like this word more than the other ones. Okay, but as I say, it's okay. It's not about my liking or disliking. Okay, okay. You can't say, Mike. Okay, but you told us, okay, as that resolution was your favorite. Why did you use the word longitudinal resolution in the question? Because I said it's not about my liking or disliking. Okay. Okay, so this exit resolution, also known as depth resolution, can also be referred to as a longitudinal resolution, radial resolution, or range resolution. You girls, unfortunately, will have to remember all these names here that they apply to the exit resolution. So that box with your synonyms on your page is 146 in your book. Make sure that you know all those names. They even make a mnemonic, LARRD. Now you say, well, okay, LAR, what the hell is that? Okay. You can make up your own mnemonic. You can say, okay, I don't like RAL. I just would like, okay, as RAL or something like that. That's fine. As long as you know that's going to be axial, longitudinal, range, radial, and depth. Are the same resolutions? Yes, you should be good. Did that make sense? Now the question is your axial resolution, is that adjustable? No. Okay, mainly because primarily as what we will say is that yes, your axial resolution, or we can say the spatial pulse length is primarily as determined by the source. So unless you change your transducer to another transducer, which may have as a shorter or longer spatial pulse length, your axial resolution is not going to change. Is that clear? So if your spatial pulse length is produced by the system was 5 millimeters, it will have an axial resolution of 2.5 millimeters, which mainly means that as long as the distance between two structures, shallow and deep, is 2.5 millimeters or more, you will get as a good axial resolution. Did you girls get that? Whereas, yes, if the numerical value is if you had that 5 millimeter pulse, produced by the transducer, now the axial resolution or the numerical value for that axial resolution is still going to be 5 divided by 2, which becomes 2.5 millimeters. So if the distance between two structures, superficial and deep, is less than 2.5 millimeters, that transducer will give you a poor axial resolution. So you want to just see those structures separately. You may have to use a transducer with a shorter spatial pulse length, because that shorter spatial pulse length is going to give you a lower numerical value for the axial resolution. And we say, the lower the numerical value was, the better the resolution. which may mean that, okay, as if you have a pulse with a shorter length, it will have a lower numerical value, right? Okay. And that lower numerical value mainly will mean that, okay, yes, it will be able to just, okay, distinguish, show you two structures which are placed closer together. Okay, so your numerical value is going to, as okay, be compared to the distance between the structures to determine whether you get a good resolution or a bad resolution. Did that make any sense?
Yes.
Yes.
So okay, so because practically, yes, okay, we can mainly say that, okay, yes, the numerical value of the axial resolution is going to be, as okay, your spatial pulse length. Oh, what the hell? So, divided by 2. Now goes, okay, let's just clean this up. So we can say, okay. The actual formula of calculating, yes, okay, your numerical value for the axial resolution is spatial pulse length divided by 2. But what we also can say is, okay, the axial, yes, okay, axial resolution's numerical value. Well, okay, yes, divided by 2. But the question is, okay, as what is going to, yes, okay, determine our spatial pulse length? How was that make? What was your spatial pulse length? How did we calculate your spatial pulse length? Because that's okay, the number of cycles per pulse, right? Okay, how many cycles did we have in a pulse? Multiplied by, yes, okay, the wavelength. Did that make sense? Where we mainly can say, yes, okay, that your spatial pulse length is mainly, yes, okay, going to be, yes, okay, directly proportional to both of these. The number of cycles. And it's also going to, it's okay, going to be, it's okay, directly proportional to your wavelength. Because, okay, if you had a cycle or if you had a pulse with a great number of cycles, that will increase your spatial pulse length. Or likewise, okay, yes. Or if you have a pulse with, okay, yes, where the cycles had a great wavelength, that as well will, yes, okay, increase your spatial pulse length. Right, okay, which actually is, okay, will increase, yes, okay, the numerical value of your resolution. Did that make sense? Whereas, okay, we could say, if you have a pulse with either, yes, okay, a low number of cycles and or, yes, okay, that each cycle had, okay, yes, a low wavelength, a small wavelength, that will mainly mean that, okay, as you will have a lower spatial pulse length, which mainly will mean that, okay, as you will have a lower numerical value for the axial resolution. Did that make sense?
Yeah.
Now, but you may be asked, what if two pulses, Baby says, okay, Baby says that one has a low pulse duration and two, or the second one has a great pulse duration. And they may ask, yes, okay, which of these two here, okay, will give you, yes, okay, good and bad axial resolution. Now just look here, girls, because, okay, what was your pulse duration? Your pulse duration, yes, okay, does mean that's okay, just the, again, yes, okay, the product of two things as well. Where one was, well, okay, sorry, the number of cycles per pulse. But when we calculate, okay, the pulse duration, the number of those cycles in the pulse was going to just, okay, be multiplied by the period. That will give us, okay, as a pulse duration. So we can mainly say, okay, if for instance, okay, we had a pulse with, okay, as either a great number of cycles, or as, okay, that the cycles had, okay, as a great period, that will mainly lead to a great pulse duration, right? Whereas, okay, as on the other hand, if you said, if we had a pulse which, okay, as with a low number of cycles, or as, okay, if those cycles as, okay, had a low period or shorter period, that would eventually as, okay, lead to as, okay, a lower pulse duration. Clear? And what did we see here? We already have talked about this. This and this, yes, okay, that was okay, because yes, okay, common factor between, yes, okay, the pulse duration and your spatial pulse length. Right? Okay. There, okay, the factor that was, okay, as not common between the two was, okay, as the wavelength and period. But what we already know is that, okay, as goes, since period is directly proportional to wavelength, that will mainly mean that, okay, yes, the pulse with a greater wavelength will, okay, have a greater spatial pulse length. And will also just, okay, have a greater pulse duration. So we can maybe says, okay, the lower the pulse duration, the lower is okay will mainly mean that okay as you have a with a lower wavelength, and due to that lower wavelength, you will have a lower spatial pulse length, which will mean okay you will have a lower numerical value of the axial resolution. So yes, okay, a pulse that actually is okay measures shorter in time will have okay as a shorter spatial pulse length, which will have okay as a lower numerical value of the axial resolution, and have okay as a better axial resolution compared to as okay a pulse with a compared to as okay a pulse with a greater volume, greater period, because that's greater period will actually mean that okay you have a greater wavelength. That greater wavelength will mainly mean that okay as you end up with okay having a greater spatial pulse resolution, greater spatial pulse length, sorry, which mainly mean that okay as your numerical value for the axial resolution will be higher, and the higher the numerical values, a numerical value for the resolution, the poorer is it that the resolution will be. Clear? So that's okay. Although that's okay, we really can't use that's okay the space, that's okay the pulse duration to just okay calculate the actual numerical value of your axial resolution. But we can say it's okay a pulse with a greater period will have okay as a greater wavelength. That greater wavelength will cause okay as the spatial spatial pulse length to be greater, and that greater spatial pulse length will give us okay as a greater numerical value of the axial resolution, and that greater numerical value of the axial resolution will lead to as okay a poor ER. Whereas okay on the other hand, we said a low period will lead to yes okay a low wavelength. Low wavelength will mean low spatial pulse length. Low spatial pulse length will mean low numerical value of the axial resolution. And low numerical value of the axial resolution is more likely to give us okay as a good axial resolution. But we would only have a good axial resolution if the numerical value of the axial resolution is, we can say it's okay, lesser than the distance between two structures, which we're going to be as okay, shallow and deep. Only then will we have a good axial resolution. Right. So if your spatial, if the numerical value of your axial resolution, for instance, is okay, was calculated out just okay 3 millimeters. But the distance between is okay the two structures was 2 millimeters. Then we have a poor axial resolution. Whereas if you can say it's okay, if it was the same structures with the same distance of let's say 2 millimeters, but the numerical value here was okay as anything less than 2 millimeters or even equal to 2 millimeters, even if it was as okay 2 millimeters, because that's okay, that okay was okay as at least that's okay a good axial resolution for these two structures here. because, okay, sorry, well, so it's getting a little cloud here, but if we can say, okay, that the numerical value or your exit resolution, even as, okay, if it was 3 millimeters, you would still have, okay, as a good exit resolution if the distance between the structures was 3 millimeters or more. So as long as the distance between the structures that you want to view is greater than the numerical value or your spatial resolutions, primarily as, okay, axial resolution, lateral resolution, and, okay, as we will talk about later on, elevation resolution. If those numerical values are lesser than the distance, it will always give you a good resolution. Clear? But for your axial resolution, please remember, girls, it's going to be okay. It's only going to be okay. We can say okay, accounting for okay, the distance between the structure that lie on top and about, or shallower and deeper, shallower and deeper, shallower and deeper. Did that make any sense at all? Right, girls? So if we look at a scanning, let's say it's okay, we are scanning an area like this is the actual area that we are scanning. This may be as okay, a traffic light from another country, where they really want you to, that's okay, abide the traffic rules. Okay, but let's say it's okay that these are structures that we can mean it's okay, as you see, it's okay. That if we go down here or we go down here, it's okay, the depth increases, right? And if we are able to see these structures shown up separately because it's okay, they lie shallow, and we just go deeper and deeper and deeper. That would mainly mean that, okay, yes, we had a good exit resolution. How is that good exit resolution produced? Mainly because, okay, the pulse was short enough that, okay, yes, when the pulse came, it went back. Brought this info, produced it on image. Then the next pulse means, okay, go deeper. You know, short enough means, okay, just to scan this information, bring it up, and, okay, show it on the image. And so on. Did that make sense? Or we can mean it says, okay, this is how the pulse came. And go back. Pulse comes, go back. So they were short enough. Not too, yes, okay, as I may say, as it comes, that it goes, and okay, as it's a long pulse. Or you could say, okay, that would have been, yes, okay, a long pulse. Then it may, yes, okay, going to mix up the red and green. And that will be as okay, a poor resolution, or as okay, cause for excellence. Yeah, because you can say, okay, these two structures, okay, which were physically as okay separate, but we see them as okay being mixed up together. Did you girls get that?
Yes.
Yes.
Yes, yes.
So you can mainly says, okay, if I look down the street, right, okay, if I look down the street and I'm able to, yes, okay, separate the cars, or see the cars separate, yes, okay, they are parked in a lane, for instance. Now me is okay, that will be a good resolution. Clear? Right. Whereas if you see, it's okay, the color of one car is okay, and then it's okay mixed with another, or you're not able to distinguish two cars that are parked behind one another. You're okay, that's a poor resolution. Clear? Okay. And the factor that determines it here is going to be as okay, your spatial pulse length. So at least out of this, okay, these three resolutions that I talked about here, that's okay. Let's remember, dear girls, it's your exit resolution that, okay, because it's okay that the exit resolution is going to be determined by the pulse. Clear? Okay. Physically, yes, okay, the longer the pulse is, well, okay, we'll have, okay, as a greater exit numerical value. The shorter the pulse is, it will have a lower numerical value. The lower the numerical value, the better is it that the resolution will be. Right, okay. Because if I, for instance, okay, yes, okay, I have a high exit resolution, or I have a high numerical value. That mainly, yes, okay, I may will say, yes, okay, well, there has to be at least this much distance between structure superficial and structure deep for me to be able to see them as two distinct structures. If they come too close, I will not be able to distinguish them. Did you girls get that? Okay. Any questions? Clear? But as okay, you still as okay, and you will have to, yes, okay, we can say yes, okay, remember you will have to remember the relationship between spatial pulse length and pulse duration. We already, yes, okay, did that in chapter number 4. So, but for here, yes, okay, it was just a revision. Because you can be given a question where you're asked two pulses, shorter, longer pulse duration, which will have the best or poor exit resolution. So if you know that, okay, as your pulse duration is directly proportional to your spatial pulse length. Spatial pulse length directly proportional to the numerical value. What the numerical value is going to be, yes, okay, you can put it as okay, inversely related to, yes, okay, the accuracy. Or you can say, yes, okay, the greater the numerical value, the poorer will be the resolution. Okay. Or another thing that you can be asked, well, okay, this is your spatial pulse length. This is the distance between, yes, okay, two structures. Now, one thing that you have to, yes, okay, watch out for is that those structures have to be lying superficial and deep. And they may say, well, okay, would you have a good Excel resolution or a poor Excel resolution? Now that can only be determined if they give you the distance between, yes, okay, a superficial and deep structure. Yeah. Only is it that you will be able to say, yes, okay, that this pulse length here gives me, yes, okay, a poor Excel resolution or a good Excel resolution. Because from that pulse line, you will calculate your numerical value of the Excel resolution. How? Just divided by 2. And if that numerical value of your spatial pulse number is going to be as okay, 5 millimeters pulse, numerical value, 2.5 millimeters. 4 millimeters pulse, numerical value for your Excel resolution will be 2 millimeters. So yes, okay, if that numerical value is equal or lesser than the distance between the 2 structures, you get a good Excel resolution. Whereas, okay, if the numerical value is greater than the distance between the 2 structures, lying deep and superficial, you will have a poor Excel resolution. Did you girls get that? Did you girls get that?
Yes.
Okay. Now, ladies, it is not directly written in the book, but please keep in mind your Excel resolution remains constant. Is that clear? Okay. So if it says that's okay, 2.5 millimeters, well, okay, that's going to be 2.5 millimeters. Clear? Because, okay, what we actually use is, yes, okay, or yes, okay, to determine, yes, okay, the Excel resolution is the spatial pulse length of the, yes, okay, produced by the transducer, which remains constant. Okay. Yep. Any questions? Okay. Now, girls, you probably, as okay, may remember. If not, then, okay, let me just refresh your memory. That I once said, high frequency transducers were, or not were, are ideal for imaging. Did you guys remember that?
Yes.
Good. And that is actually, yes, okay, going to be, yes, okay, very, yes, okay, just confirm now. Why? Or we can mean it as, okay, why is it that high frequency transducers are going to be, it's okay, ideal for diagnostic imaging? because these high frequency transducers here, yes, okay, have a short wavelength, right? Right?
Right.
If somebody still is in doubt, but well, okay. We know that, okay, as frequency is inversely proportional to wavelength. So it's okay if your wavelength is great, or your frequency is high, you will have a short wavelength. And what is this short wavelength going to give you? This low wavelength, what does that give you? Take it step by step, and okay, so it will make sense.
Will the wavelength give a lower spatial length?
Exactly, very good. Okay, so that will give you as okay a lower spatial length or spatial pulse length, right? What will that lower spatial pulse length give you?
A lower numerical value?
Of okay as the axial resolution, right? Right?
Yes.
Good. And what did we say about as okay a low numerical value? That will give us okay as a
Resolution.
good or better resolution, right?
Yes.
So that's why as okay I said back then that okay as for diagnostic imaging, high frequency transducers are, because it's okay, the higher the frequency, the better. But just keep in mind, go that okay, as good is good, but too much good is bad. Because it's okay, too high of a frequency, what is that going to cause?
No image.
Huh?
I said no image.
Okay. You are correct, but how?
It's not going to be able to penetrate. It's going to keep going.
So you can make it says, okay, if the frequency is too high, there will be as okay, no penetration. No penetration may mean that okay, as the sound wave will not make it to the person's or patient's body. So if no sound travels into the patient, well, okay, no sound is going to reflect back. At least, okay, as if it reflects back, well, okay, it's not going to bring you any info. And if you don't get any info, yes, okay, then you don't get an image. Right? It's just like, okay, it's using a binocular, but it's okay if you cover the front pieces of the binocular with plastic, that's okay, don't take off the covers. Well, okay, you don't see anything. Right? Did that make any sense? Okay, so that's why, yes, okay, we said, okay, yes, for diagnostic imaging, well, okay, there was an upper limit, 15 megahertz. Because if it goes beyond that, that's mean you're going to cause that, okay, as the sound wave is going to just, okay, attenuate even before it hits the person's body. Did that make sense? But based on that, we can mainly say, okay, that higher frequency transducer is ideal for, yes, okay, diagnostic imaging. Why? Because the higher the frequency, the shorter the wavelength. The shorter the wavelength, the shorter will be, yes, okay, your spatial pulse length. The shorter that spatial pulse length is, well, okay, you will have a lower numerical value for your axial resolution. And the lower the numerical value for your exit resolution is going to be, well, okay, the better is it that exit resolution will be, which means it will mean that, okay, yes, it will be easier for us to clear, yes, okay, distinguish structures, even though, yes, okay, they are placed close together, which would have been, yes, okay, unlikely to happen had we had a low frequency transducer, because that low frequency transducer will produce sound waves with greater wavelengths. Okay, or because that's okay, now that greater wavelength will most likely is okay lead to a greater spatial pulse length. That greater spatial pulse length is okay, even if you divide it into half, it's still going to is okay become a greater numerical value for your exit resolution, which will cause it to be, or likely it's okay to be a poor exit resolution. You can still have a good resolution, okay? But that is again going to be dependent, okay, as what was your numerical value compared to the distance here? So as okay, you can say it's okay, the lower the frequency goes, the greater will the wavelength get, the greater will the spatial pulse length get, the greater will be as okay, the axial resolutions numerical get, and okay, as there's going to be as okay, a greater probability that okay, yes, it will not be able to as okay, distinguish between these structures here at some point. And they will actually start to get smushed together. Did that make sense? Okay. So whether you just want to just okay, memorize it, or maybe it's okay, use your yes, okay, good old concepts. Higher frequency, higher wavelength. And we just did okay as what the effect of those higher wavelengths was going to be on your spatial pulse length. On a spatial pulse length, okay, as on the exit resolution's numerical value. And we said, okay, the higher the numerical value of an exit resolution is going to be, okay, more likely is okay to produce a poor resolution or exit resolution. But it's still going to be as okay, comparing as okay, the numerical value, 2 millimeters, comparing that to yes, okay, the distance between the two structures. So that was one thing that, okay, yes, your book says, okay, yes, what gives you, yes, okay, good exit resolution. And, oh, yes, okay, on the other hand, because I will give you, yes, okay, poor exit resolution. Now, go, your book also, yes, okay, uses a word or a term that it says less ringing. We can mean, okay, that this less ringing here. Okay, let's just use two colors. That's why we can say it's okay, less, okay, sorry. Okay, just because, okay, now the ideal situation, okay, let's just say ideal is okay, good. Green is good. It's less ringing. Now the question is okay, what do you mean by less ringing? Okay, now go what less ringing mainly is okay, just means is, I guess it's okay, a less number of cycles per pulse. And what is that going to do? No, you can mean it's okay, just look at, okay, as your spatial pulse and I say it's okay. If we have, okay, as a less number of cycles in a pulse, or we mean it's okay, can just say it's okay, they may have, okay, as a fixed wavelength, let's say it's okay. 2 millimeters, for instance. Let's say, okay, here this less number of pulses, cycles in the pulse is 4. But okay, yes, the spatial pulse length in this case, yes, okay, will be 8 millimeters. Where, okay, yes, if we just divide that by 2, yes, okay, it just gives us, okay, yes, 4 millimeters, which is going to be, yes, okay, the AR's numerical value. Now let's just compare this to, yes, okay, the opposite. That we can see as okay, we can say, okay, more ringing. So what is this more ringing here going to mean? Now, I mean, that means, okay, we will have, okay, it's a great number of cycles or pulse. So we can just take that and say, well, okay, what if we is okay had a greater number than 4? Let's say it's okay that we had, let's say it's okay, 6 cycles per pulse. Where each pulse, where each cycle still had, okay, as a wavelength of 2 millimeters. Because we just want to, okay, fine, okay, what's going to be as okay the effect of more and less ringing in terms of, okay, as poor or bad axial resolution. Now we can mainly say, okay, here is okay, your spatial pulse length is going to be, as okay, 6 cycles. Each cycle has a wavelength of 2 millimeters. So that's going to be, as okay, a spatial pulse length of 12 millimeters. Now, if you divide that by 2, well, okay, as you can see, it's okay, our axial resolution numerical volume here is, or value here is going to be 6 millimeters. But I hope that everybody can agree that, okay, yes, that 6 is a greater numerical value than 4, right? How did we get 4? Yes, okay, mainly because of less ringing. How did we get 6 millimeters as the axial resolution's numerical volume? In this case here, mainly because of a pulse which had more cycles in the pulse. Did that make sense? I just put it as, okay, yes, less ringing of your phone. Let's say each time your phone go ring, that's 1 cycle. Ring, okay, that's another cycle. The sooner you pick up the phone, what is it that your phone is going to do? Ring less. Or you can say, okay, your play or your ringtone is going to be as okay, just play a less amount of time. Right? Whereas if you let it ring, it's going to go on ring, 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 ring. So that will be more ringing, right? And if you haven't set your phones, yes, okay, go on to the answer machine. It may, yes, okay, keep on ringing Yes, okay. You are say, okay, okay, I can't talk right now, or you pick up the phone. Clear? Okay. But here is okay, the main is okay, just use the phrase as of less number of cycles, they mean it's okay, just use the phrase less ringing. Okay. Clear? So yes, okay, the sooner you pick up your phone, yes, okay, the less time is it that it will be ringing. Okay, because it's okay, each time that your phone rings, ding, it's one cycle. Any questions? So either, yes, okay, you have less ringing, which is just okay as a fancy word of saying less number of cycles per pulse. Will give you, yes, okay, a good exit resolution. Why? Because less number per pulse, well, yes, okay, cause the pulse to have a shorter spatial pulse length. Shorter spatial pulse length would mean lesser numerical value of your exit resolution. And the lesser the numerical value is, the better will be the resolution. On the other hand, we say it's okay, high frequency. So high frequency, well, you can always, okay, you will have to relate that to, yes, okay, high frequency will be low wavelength. Low wavelength, low spatial pulse length. Low spatial pulse length, lower numerical value of the exit resolution. And the lower the numerical value of the exit resolution, greater will be the likelihood that it gives you, yes, okay, a good exit resolution. Does anybody have any confusions left? And or you can also just, okay, say that greater frequency will lead to, just, okay, a shorter period. So where you want, just, okay, relate, just, okay, high frequency to better exit resolution in that way. Okay, because period and frequency were inversely proportional. So were wavelength and frequency, right? Which made frequency and which made wavelength and period directly proportional to one another. Okay, but just please remember, ladies, that wavelength, period and frequency were not only as okay inversely proportional, they were also reciprocal. Right? So what would be the period of a cycle if your frequency was 2 megahertz?
A half.
A half what?
A half of a period.
No,
B hertz.
no.
No, period is time.
Time, right?
Second, sorry. So half of a second.
If it's megahertz, it will be half of a second if your frequency was 2 hertz.
Is it a nanosecond? No.
No, my dear, not a nanosecond. You went a little bit too far.
Sir, can you repeat how much hertz, how much megahertz, what, 2 megahertz?
2 megahertz. So if your frequency was 2 megahertz, what is the period? Shaq already gave half of the question, which is half. We just have to get the right unit of time.
Oh, time.
And you said nano is
One
going too far,
second.
right?
Nanosecond is too far off the scale, my dear.
A
Okay.
microsecond.
Is it a millisecond?
Microseconds.
It will be a microsecond. So
Yeah.
half a microsecond.
Thank you, Marianne.
Someone else said it too.
Okay, but if I say as okay, 2 kilohertz, then your period will be half of a millisecond. Okay, if we say yes, okay, it's just 2 hertz, that may mean yes, okay, 2 cycles were completed in a second, right? So if something yes, okay, is completed in 1 second, the time for each of those events will be half of a second. Now, some people may have a long ringtone. Have you heard that? That's okay as half of a 5-minute song that has been so yes, okay, there are 4 rings. That's out now, but like okay, when okay, yes, that was in the first place as okay, was something new. Okay, so you could say okay, that will have been okay as a long wavelength. Right, okay. Or you can say okay, a long period for which the ringtone will go on. But generally speaking, yes, okay, less ringing, yes, okay, is just okay as another, yes, okay, fancy word of saying yes, okay, less number of cycles per pulse. And then you mean it's okay, the other word means yes, okay, be the frequency. So less ringing and high frequency, low spatial pulse length, or is okay, in this case, we can say okay, will lead to or give you a low numerical value for the Excel resolution, which will lead to as okay, a good Excel resolution. Where you will flip either of them or both of them in the opposite direction, that will lead to a poor Excel resolution. So more ringing and or high frequency will lead to a poor Excel resolution. Okay, either or both. Does anybody have any doubts about the Excel resolution? The numerical value of your Excel resolution? Spatial pulse length divided by 2. Clear. How do we calculate the spatial pulse length? The number of cycles multiplied by the wavelength. Clear. Okay, girls. So you got 12 questions or review questions on page 149 and 150. Yes, Maria?
So on 147, I don't know if I missed it. Did we do the actual resolution of, it says 0.77 times?
No, don't worry about that one.
Okay.
Okay. So it's made as okay, just your exit resolution divided by, oh sorry, exit resolution equals to your spatial pulse length multiplied divided by 2. Right? Right. Okay. Spatial pulse length divided by 2. What was your equation for your spatial pulse length? Number of cycles multiplied by the wavelength of each cycle. Clear? What determines your wavelength? In the source. Now we said source, right? Always, okay, wavelength was determined by both source and medium. But in the medium, it's going to be as okay, the change in speed of sound that will change the wavelength. But here it's okay, we keep it constant. Okay? Here we keep it constant. Now it goes in your transducer, what was going to be the component that determines your wavelength?
Is it the PZT? The
How many?
PZT?
PZT, exactly. Clear? So when we, yes, okay, in chapter 3 said, determined by source. Now we know source, transducer. Now we know even further, which part of the transducer? The PZT. Will be as okay, the main component of the transducer that determines the wavelength of each cycle. And since it determines the wavelength of each cycle, it also is okay, determines the period of each cycle. Is that clear?
Yeah.
Good.
Yeah.
Now may I ask another question then? So that was your period and or wavelength of your cycle. What will determine the number of pulses or number of cycles, sorry, per pulse? What component will determine the number of cycles that you have in a pulse?
Component of like the transducer?
Yes, my dear.
Okay.
Now, students, is not directly mentioned in your book. So don't go back to chapter 8 and see if you can find that explanation. When I say not directly, you'll not find, okay, this is going to be the part that determines the number of cycles in the pulse. You'll not find that word. But if you read upon the component and look into it, it is indirectly, yes, okay, going to be mentioned. Or you have to think a little bit and then say, okay. So is there anybody who has a guess?
Is it the pulse duration?
No, my dear.
Is it the damping material?
Exactly. Exactly. Very good, Dr. King.
Thank you.
The backing material. Because had it not been for the backing material, what would have had? Continuous cycles, right?
Yes.
It's the damping material that says, well, okay. Not that many cycles. Let me absorb some of those cycles and just send out pulses. Did that make sense?
Yes.
Or had it not been for the backing material, what would have happened? Non-stop cycles, right?
Yeah.
It's the backing material that says, okay, cool down. And the more it cools it down, yes, okay, the shorter is the deposit that's going to be, because the backing material is okay. Media is okay, reduces the numbers of, because it's okay, sound wave produced by the vibrating PCTs that actually is being sent ahead as a sound pulse. Yes. So you can see it's not everything that is directly mentioned in the book. You may have to read it once, twice. Twice, okay, think upon different things. And okay, that's what I'm trying to give you goals. That's okay, the way to think upon. Or it's okay, give you the information. Pretty much okay as pick it up with a spoon and feed it. Now, who is in the mood for a break?
Me.
Okay. Okay, go. So yes, okay. Did your exit resolution? You have some good 12 questions. So you can take your lunch. Hallelujah. And you can have some time to just, okay, try to answer these questions as well. Okay. So would it be fair that I say that I see you girls back at 1 o'clock?
Yeah.
Okay,
And now, girls, please try to just, okay, use the time to answer these questions. Although it's okay, we'll be go over them together. Okay, but you say, okay, these will be the questions that I will be asking Dr. Mike when we come back. We'll
okay.
have them ready. Okay.
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 Thank
See you
you.
then. Okay, you're welcome. Then. Welcome back. Okay. So let's just try to do these this dozen of questions here together, and then you'll be off. Okay, girls? Yep. Now, any questions that are giving you a hard time?
Question 5.
Okay, so okay, somebody said question 5. So, okay. Anybody else had a question that was giving a hard time? Okay, let's see. So the first question, which you find on page 149. Question 1 mainly is, okay, yes. What is the ability to accurately distinguish two structures lying close together? That was what we called resolution. Clear? Where it says, okay, that lying close together in depth. Okay, then that will end become, yes, okay, you were axial resolution, which we also call longitudinal resolution, range, radial, and depth. Oh, that's me. That's okay. What question 2 asks about? Okay. So again, yes, okay. Question 2: the ability to, yes, okay, distinguish two structures that lies close together, front or back, and that's why it says, okay, that means, okay, that's a word that your book uses. Okay, front and back. Okay, or please, ladies, make sure that you remember this one here. Parallel to the beam's main axis. Okay, it's called, that kind of resolution could be called accuracy of this, okay, ability to this, okay, accurately distinguish would be as, okay, axial resolution, longitudinal resolution, range resolution, depth resolution, or range resolution. Clear? Question number 3. Now, axial resolution is measured with the unit of, and that's going to be, okay, distance. Not just your axial resolution, even, yes, okay, when we, yes, okay, on Monday talk about, yes, okay, our lateral resolution, you will see that that's also going to, yes, okay, be measured in a unit of distance, which is going to be the same, centimeter, millimeters, micrometers, whichever. Clear? So is, okay, as your elevation resolution. Okay, so that's also going to be, as, okay, referred to as, okay, a measure using, yes, okay, a unit of distance. Clear? Now we can go on to question number 4. Now, if there are more cycles in a pulse, okay, so it says, okay, if we have, okay, as a great number of cycles per pulse, right, okay. Now we says, okay, the numerical value of range resolution. And that's why I said, girls, that, okay, please make sure that you know that also like a range resolution, that's what I mean, is, okay, that's what we also call the axial resolution. So here is, okay, they didn't use the word range axial resolution, but the meaning is, okay, just replaced it by another name, which was the range resolution. They could have placed it with range, radial, longitudinal, or depth resolution. Yeah. It's going to be greater, lesser, or the same. Now just keep in mind, girls, greater number of cycles. Because says, okay, this greater number of cycles will also have been the same as saying, yes, okay, more ringing. But what was that going to do? That was going to just, okay, increase your spatial pulse number. Clear? Which for me, that's okay, just increase the numerical value of, okay, as your range resolution. Clear? Although not asked in this question, but we can take it a step further and say, yes, okay, that will cause that the resolution is degraded. Or you have, okay, as a poor axial or range resolution. Yeah, so your numerical value, yes, okay, that's what they ask is, okay, that's going to increase if you increase the number of cycles per pulse. Did that make sense?
Yeah.
Good. Okay, question number 5. So let's see. Now, if a new pulse transducer has many more cycles in its pulse, so what they mean is, okay, just say is, okay, what they mainly mean by that, okay, is if we use a transducer with increased number of cycles in the pulse. Now, previously, okay, from the last question, it's okay, but can we see? Okay, yes. What they may ask, okay. The image accuracy, is that going to be improved? Is that going to be degraded? Or is that going to remain the same? Now, mainly, it's okay, from this, you can say it's okay, in the greater number of pulses, what would that lead to? A greater number of cycles in a pulse, sorry. Now, I mean, yes, okay, in this case, it looks as though you have, okay, as a greater spatial pulse length. Clear? This greater spatial pulse length will mainly mean that you, okay, as end up with, okay, as a greater numerical value for the axial resolution. And what I said, that the greater the numerical value of any of these as, okay, resolutions here, especially as, okay, the ones that we put on the spatials, will lead to a degraded or poor resolution. Did that make sense?
Yes, now it did, yes.
Clear? Okay. Okay. So yes, okay, if you don't directly know, you can always, okay, just go tick, 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 this indirectly here. Okay. But you can mainly, as okay, you can mainly, as okay, just rewrite it and say greater, yes, okay, the numerical value of the resolution. That will lead to a poor, or we can say it's okay, the greater resolution. Whereas, okay, yes, just the opposite would be the lower numerical value of a resolution. Now, meaning yes, okay, that you have, okay, it is okay, good. Or in this case, that's okay, you may even say it's okay, an improved resolution. Okay. So in the previous question, for the media, okay, that says, okay, is a longer pulse. Is that going to have a greater or lesser numerical value? Greater pulse, greater numerical value. Lower pulse, lower numerical value. Okay, then the next question, on question 5, the main says, okay, same as, okay, greater pulse, would that lead to a good resolution or a poor resolution? Now, the greater the numerical value means, okay, due to greater pulse would mean that the resolution will be poor or degraded. Did that make sense? Okay. Okay, guys. Question number 6. So high or low frequency transducer usually, yes, okay, generally have the best range resolution. We just did that earlier before the break. We said, okay, high frequency transducers. And what they mean is, okay, let's say with this high frequency transducer, would that lead to a good or best, whichever, range resolution? Now just keep in mind that, okay, a range resolution is okay, that was just another name for your axial resolution. And they could have used any other name. They could have used radial resolution. They could have used longitudinal resolution. They could have used depth resolution. Obvious, okay, pretty much, okay, has already established that, okay, yes, directly either as, okay, just remembering, or because that's, okay, this great frequency here, or actually just, okay, a lower wavelength. That lower wavelength, lower spatial pulse length, lower spatial pulse length, lower numerical value of, that's okay, for me, in this case, I had range resolution. And what we already, yes, okay, have said that, okay, yes, a low numerical value will lead to, yes, okay, a good resolution. Okay. So I just ask you to choose as, okay, which kind of frequency do you want? Or good. If they ask about as, okay, we'll give you as, okay, a poor range resolution. Then you may as, okay, should choose that, okay, a low frequency transducer will lead to a poor range resolution, or radial, or axial, or longitudinal, or depth. Why? Because that's going to cause a great wavelength, which will lead to, okay, great SPL. Great SPL will lead to, okay, a great numerical value of this resolution here, which is going to, okay, when the numerical value is great, lead to poor. Did that make any sense?
Yes, it did.
Question number 7. So you can see, yes, okay, usually it's okay when there are things which are, okay, as having some relations to things, you're most likely, yes, okay, will be asked high, low, things like that. Okay. Okay, we have seen that these kind of questions, okay, being repeatedly asked, that's okay, in context to different things. Okay, but you have to know, that's okay, when those relationships are relevant and when they are not. Okay, so what they say here is, okay, yes, in which of the following transducers will have the poorest axial resolution? So you can say, okay, the poorest axial resolution. That's what we are looking for. Now we already, yes, okay, said that. Okay, in whichever way is okay. This poor axial resolution mainly as okay would be as okay due to a high numerical value of the axial resolution. Where would that high numerical value of an axial resolution come from? That will come from, okay, as a great spatial pulse length. Clear? What can cause as, okay, a great spatial pulse length? Are there, okay, great number of, cycles per pulse, and or if those cycles have a great wavelength. So that's mainly as, okay, what you just will be looking for, right? Okay. Now, which one says that's okay, high number of cycles per pulse and great wavelength, or this great wavelength is, okay, could be worked as, or could be named or labeled as, or it's, okay, worded as low frequency. And this great number of cycles can also, it's okay, be called, can also be called more ringing. Clear? Okay, now what they have given us here is, okay, yes, different frequencies and different numbers of cycles per pulse. Clear? So as, okay, the first option that we have is, okay, mentioned is the frequencies. And what we need was, okay, as the low frequencies. Where did we find the low frequencies? Because, okay, that was 1.7 megahertz. That was the low frequencies, because the other one was 2.6. So maybe that's, okay, A and C. And in this we made as, okay, now just have to say, okay, fine, it's okay, which of these have the greatest number of cycles. So in A, it's 4 cycles per pulse. In C, it is 5 cycles per pulse. So that's, okay, mainly because of 5 cycles per pulse, which we find in option C will be the answer. Did that make sense? Yes, girls, did that make any sense?
Yes, it did.
Okay. Question number 8. Okay, so you can see it's mainly as, okay, if you grasp the concept. Yeah, okay. And okay, that's if you know what you want to call it, that's okay. Names for the different things may be, because they will be going, as okay, mentioned under different names. You should not have any problem of answering a question. Okay. Now, girls, please, although it's okay, you might already have done them, but repeatedly go back. Go back. Okay. My advice would be start your revision for your midterm from now on. The thing that you can revise is made as, okay, things that we already have done. You can say, well, okay, today we talked about spatial pulse length as, okay, as a major thing. Let me just go back and look at that thing in chapter 4. Okay. You can say as, okay, when looking at that, go and, okay, even look at, okay, as your wavelength, your frequency, and your period as well, because they are indirectly related to your spatial pulse length which is made okay related to your exit resolution. So that it doesn't really matter is okay how complex that question may look like in the beginning. There's always going to be as okay a very basic concept or very basic explanation for it. Why the answer it is what it is. Clear? So once you do it as okay with okay as arrows and flowcharts or spreadsheets or a couple of times, next time you see, you don't really have to, you can read the answer and even before you go to the choices, you will know what to look for. And then it doesn't matter what gets picking it out from yes, okay, the answers or choices that has been given. Did that make sense?
Yeah.
But it requires that, okay, yes, you can't say, oh, I did those questions once. Well, okay, that was 3 weeks ago, or a month ago, or 2 months ago, or so. Okay. Let me just see. Okay, I'm still able, I'm still on top of this. Okay. Question number 8. Now in soft tissue. So you can see, yes, okay. 90% or plus of all is okay questions or is okay concepts are going to be of soft tissue. Now it's okay, here they're bombarding us with a whole lot of information. So you can say, okay, in soft tissue. Okay. Now what is it we have? Yes, okay, that's going to be yes, okay at 3 cycle. Okay. Now what do you mean by 3 cycle? Or 3 cycle? That means that we have 3 cycles per pulse. The word per pulse is not mentioned, but that's mainly as okay where we should. Someone is okay assume. Okay. We have as okay 1 megahertz. That's mainly as okay your frequency of the transducer. Okay. Then the UAS okay have given us okay as what we can say is okay the pulse length. Okay. Now although goes the ASOK didn't wrote the word spatial. But even ASOK, if you look at it, it says 4.5 millimeters. So it's okay, that 4.5. I mean it's okay because it is millimeters, mean it's okay, it should tell you that okay, yes, this pulse length here is going to be as okay spatial because it is expressed with a spatial unit, a unit pertaining to space or area or distance. Did you girls get that?
Yes.
Right, okay. Now the question that they just asked you here is, okay, where is the exit resolution? Now some of you may go and say, oh, so what am I supposed to do? Because okay, for your spatial or your exit resolution, you will need to know a spatial pulse length. Now, if you didn't knew, or if you weren't able to figure out that this here, this was your spatial pulse length, you might end up, okay, doing a lot of, okay, as unnecessary calculations and math and whatnot. Because, yes, okay, what would that math be? You may say, okay, as a frequency of 1 megahertz. That may mean that, okay, as your wavelength in this case, yes, okay, now you can still do it, but that's just going to just, okay, take up a lot of time from you. Because we say, okay, wavelength was, okay, 1.54 divided by the frequency, right? You remember that equation from chapter 3? You can make this, okay, 1.54 divided by 1. So that will mean is okay, mean that okay, as your wavelength was going to be okay 1.54 millimeters. Now then you just okay, just say spatial pulse length with this wavelength is going to be a number of cycles. So 1.54 divided by 3 or multiply by 3. Well, I give you as okay, something like this. 4.5. But did you really need to do all this math? No. Because your spatial pulse length is directly or okay, in a little tricky way, yes, okay, directly given to you in the question. Now, the main thing that you just need to know is, okay, is what do I do with this spatial pulse length? Because what they mean is, like, I ask you is, what is the axial resolution, or what is the numerical value of your, okay, they were nice enough to say, okay, your axial resolution. So you may say, well, okay, that's just going to be this 4.5 millimeter, which was, okay, it's your spatial pulse length. Yes, divided by 2. So that just becomes 2.25 millimeters. So that's going to be your numerical value of the axial resolution. And what would that mean? That as long as there is at least a distance of 2.2 millimeters between this structure here and this structure here, you will have a good axial resolution. If this distance here was less than 2.25 millimeters, then you will have had a bad axial resolution. But that's how it's okay, the numerical value for your axial resolution for this transducer here is okay, was calculated. Okay. So although it's okay, you didn't have the word spatial, but you could figure that out from the value of what they refer to as the pulse length. Okay, yes, it's got to be something that's okay in space or pertaining to distance. Clear? Oh, yes, okay, you yes, okay. The other way that you could look at a pulse was in time. And if you say, okay, how long is it that a pulse is going to be as okay referred to in terms of time, that would have been okay as a pulse duration. Clear? Did that make any sense?
Yes, it did.
So that's how you may, yes, okay, you can say, it's okay, extract the vital information that is not given in the question, but you have to, yes, okay, somehow. Okay. And may say, okay, well, okay, thanks for all this, but I really didn't need that. You might have needed that, yes, okay, had you not been given this. Has this information not been given, I say, okay, well, this is a soft tissue, 3 cycles per pulse, a frequency of 1 millimeter or 1 megahertz. Then you have just, okay, calculate your wavelength, then multiply that wavelength by your number of cycles to get the spatial pulse length, and then divide that spatial pulse length by 2. Because that will give you, yes, okay, the numerical value for your axial resolution. But it's okay, the mean is okay, just gave the value that you had in the question. So very much no need to do all this calculation before calculating the AR. Question 9. Now, which of the following transducer has the best exit resolution? Now, again, yes, okay. So we can say, okay, best exit resolution. Or we can mean, okay, that best exit resolution would mean that's okay, what was going to give us, okay, is the lower numerical value of an exit resolution. Or as our book says, for best exit resolution, what we needed was, well, okay, as we say, this lower value was going to be, okay, a low spatial pulse length. How do we get that? From a high frequency and less ringing, which may mean less number of cycles per pulse. So that means that's okay, what you need to choose. Clear? Now here as okay, it's pretty much okay at the same values that we had in okay as the question 7. But here's okay, we may as okay need to look for the one with the highest frequencies. That's how you do your okay elimination, right? Okay. You can say okay, B and D were being the one with high frequencies because in both cases, okay, the frequency was 2.6 megahertz, which is greater than 1.7. Which were are because they were going to be low frequencies. Clear? And then we just have to look, okay, as which between B and D has just okay the less number of cycles. Because all the meaning is okay, we'll call less ringing, right? Okay. So that's okay, B has 3. And D as in donut has 2. So this will be the one with less ringing amongst these two. So option D with a 2.6 megahertz. And okay, it's 2 cycles per second, or per pulse, sorry. Will produce the shortest of all these pulses, which will mean lowest value of a numerical value of the exit resolution, which will mainly mean that will be the best exit resolution. Why? Because of a lower value, which may mean that okay, it will be able to distinguish 2 structures that are more closely placed to one another. Did that make any sense?
Yes.
Good. Question number 10. So 2 different transducers create sound pulses. Okay, so we can make it, okay, just say, so we just label them as, okay, transducer A and transducer B. Okay, one transducer is labeled as, okay, 5 megahertz and the other is 3 megahertz. So we can say, okay, what are we having? Frequency. So we have, okay, as 5 megahertz and we have 3 megahertz. Clear? Now, which transducer is more likely to create a more accurate image with respect to exit resolution? Which transducer probably have the lower numerical value of exit resolution? So here they're asking us 2 things. Mainly as, okay, which of these 2 is having the best exit resolution? Clear? Likewise, okay, yes. Which of these 2 here have the lowest numerical value of the exit resolution? Now right here is okay, the concept that we already did. We can say, okay, the transducer with a higher frequency will have a better exit resolution. And that's also going to be as okay, the transducer that areas okay, the lower numerical value. So that's okay, the answer for both of these, whether it's talking about the best exit resolution or lowest numerical value for exit resolution, is going to be the 5 megahertz transducer. Right, okay. At the ask does the opposite and says, okay, poorest exit resolution and highest numerical value. Then that would have been the 3 megahertz transducer. Yeah. Okay, but here is okay, there are two separate things. That there are okay as best resolution or best exit resolution, but highest numerical value of exit resolution. Now for the best resolution, it was still going to be okay, the 5 megahertz. But it's okay for the highest numerical value of the exit resolution will be, it's okay, the 3 megahertz. Okay. But here it's okay, in this question, it was okay, it was a 2-in-1. Question 11. Now, two different transducers create pulses, okay? Both transducers create a pulse with a 4 megafarad frequency. So we can say, okay, transducer A and transducer B. But okay, here is okay, they have the same frequency. Both of them have a frequency of 4 megahertz. Right, okay. Now, one transducer creates pulses comprising of 6 cycles. So you can say, okay, that will be okay, to be cycles for a pulse. So you can say, okay, that's going to be 6 cycles. Whereas, okay, the other one is okay, have 3 cycles. Now again, it's okay, they're asking us the same 2 questions. Okay, which has best or more accurate as okay resolution respecting to as okay exit resolution. Second question is which has the lower numerical value. Clear? Now goes. Just look at it in this way that okay, yes, the frequency being the same in both cases, mainly or mean that okay, they both also have as okay equal wavelengths. Okay, but here's okay, that wavelength is going to be as okay multiplied by a greater number of cycles, which mean that here, what do we have? We actually as okay end up with a greater numerical value compared to over here, it's okay, where there will be a lower numerical value. So it's going to be this transducer here. A 3 cycles transducer, which has the lower numerical value. And then, okay, as that will also be as okay, the one that's going to have is okay, the best exit resolution. That makes sense.
Yes.
Which the last and the dozen. Now, two different transducer create pulses. Okay, good. One transducer is labeled 5 megahertz, the other is 3 megahertz. So we can say, okay, transducer A, transducer B. So that's okay. What do they have? The frequencies is 5 megahertz and 3 megahertz. Now, the 3 megahertz transducer create a more accurate image with respect to exit resolution. Now, what they mean is that here is okay, as now, although this one here is okay, has a lower frequency, which means okay, this one here is okay, has a greater frequency. Okay. But in spite of having a lower frequency, as okay, this is still going to be the transducer that produces a more accurate image in terms of okay, yes, exit resolution. Now, how is that going to be possible? Now, girls, just look. So let's take this guy. There's low frequency here. Yes, okay. What would that mean? That would mainly mean, okay, that would mainly lead to, yes, okay, that we will have a greater wavelength. But since it said, okay, as this pulse or this transducer here is still going to just, okay, produce an image with a better exit resolution than the one with a higher frequency. Now that can only be because that we will have, okay, as a low number of cycles. In this transducer here. Okay, we can say it's okay, low number of cycles per pulse. Although it's okay, since this one is okay, have a high frequency is okay, it will is okay, have a lower wavelength. But that may actually is okay, produce pulses with okay as a greater number of cycles per pulse, which means okay, very means okay, we say okay, the product of these two is okay here will be lower spatial pulse length, as whereas this one here is okay, will be a greater spatial pulse length. Which means okay, going to be greater because of the greater number of cycles. Or this one is going to be lower because of the lower number of cycles. Although it's okay, here we had a greater wavelength. Okay. So that's okay. That was a little bit of a focus question there. Okay. That's okay. That's although we say that's okay, low, higher frequency, that's okay, better. But that's okay, that higher frequency transducer could still produce just okay, a lower numerical value of your exit resolution. And because okay, it has lesser number of cycles per pulse. which means they'll call that, okay, although the wavelength may be longer, but the pulse ends up becoming smaller because it's maybe it's okay, a longer cycle is okay, but just 2 cycles or 3 cycles in a pulse. Compared to it's okay as wavelength or as a pulse width, cycles with a shorter wavelength, but may become greater a pulse because there's more cycles in that pulse. Okay. So maybe that's okay, twisting and turning around in the arena. So how would you exit resolution? Not that bad yet, right? Okay, go. So please read on this fellow here. Okay. And what I recommend you also do to just okay, be able to just okay, grasp on the lateral resolution. Please just read on your beam. Chapter 9. Okay. So please read on your beam. Did that make sense?
Yes.
That's mean that's okay, just the areas of the beam and something like that. You know, what's focus, what happens out of focus, so and so on. So that's okay, that may help you. That's okay when we go to the lateral resolution. Any last words of wisdom? Anybody want to say anything or ask something? Okay. Then I guess have a nice weekend. It's not outside weather, so stay indoors. And instead of reading a novel, read the green. Okay.
Okay.
See you later on Monday then.
See
Thank
you.
you.
Bye.
Okay. Stay blessed.
Have a
Bye-bye.
good weekend.
So do you.